Good morning. It's more than South Florida that is seriously threatened by climate change and sea level rise, for sure. It's all of coastal Florida, in the peninsula certainly, and in parts of the Panhandle. What I've been asked to do this morning is to go over evidence of our warming world, the consequence of that warming on sea level rise, and the effect of accelerated sea level rise on our coastal zone. A lot of the work I've done has been on the natural and built environments, but the archaeological sites are within both of those, and so the same type of solutions apply, as I'll try to outline today. I'll show you a few examples of threatened sites and what our options are, and then conclude with sort of what you can do. And I point out to begin with, being here now is a positive step. It's what we need, is more participation from folks, all stakeholders on this topic. So I was going to use a pointer, but I can't really, so I'm going to try to use this because I like to point out stuff. So anyway, this is a picture down in South Florida during the king tides. I'm sure you've heard about them there. They have terrible issues. They're just a few feet above sea level. All their stormwater systems are gravity drained. So both seawater comes in through the stormwater system during extreme high tides, and during heavy rains the water backs up and can't flow out as fast as it was initially designed. Clearly they didn't build these streets at these elevations and have not been facing these for the last 100 years. This is a consequence of rising sea level. So as background on climate change and evidence, here's a classic. Down here on the x-axis is time back 400,000 years, and then there are three parameters that are being tracked here. Global temperature, it's just relative to present, CO2 concentration, and sea level. This information was derived from ice cores taken in the Arctic and Antarctic, where they now have ice cores that are 2 or 3 kilometers in length. They slice them up in little centimeter-like intervals, and it's snow originally, and they find little air bubbles in there, and they can actually measure the concentration of gases in that are proportional or representative of the atmosphere at the time. And based upon this, they've gone back now more than 400,000 years. But let's start with this one here. This is CO2 concentration, and what they noticed is that there were these cycles of high CO2, low CO2, high CO2, low CO2. And those parallel temperature. When CO2 concentrations are high, so is temperature. This is the greenhouse effect. When you have high concentrations of CO2, incoming solar radiation makes it through the atmosphere, upper atmosphere, down to the Earth, but it is absorbed by the Earth and re-radiated out at a different wavelength. And now that wavelength can't get through as efficiently, so it is trapped like a greenhouse. And what you can see is when, when the CO2 is high, temperature is high, and sea level is high. Because when temperature rises, all the landlocked ice melts, and it goes into the oceans. When the temperature falls, all that water evaporates and is stored at high latitude and altitude, and it is removed from the ocean and sea level falls. And the scale of this is 300 feet or more. 15,000 years ago, during the last sort of glacial maximum, see, temperature is low, because CO2 is low, sea level is low. So 15,000 years ago, sea level was 300 feet lower than it is today. And we moved into a warming period. The ice melted and sea level has risen 100 meters in less than 15,000 years. And it basically stabilized about 3,000 years ago. Sea level had stopped because most of the melting, the climate had come into equilibrium. But what we can see now, if we look at CO2 concentration today, it's up here. Never It said, I checked, 406 parts per million today. Never in the past 400,000 years or more has it been that high. So the two things that demonstrate that the climate is changing and is caused by human are the magnitude of changes and the rate of change. That magnitude is greater than any of these, and it's vertical, happened instantaneously. Magnitude and rate of change demonstrate the climate is changing and humans are responsible. Here's the next set of drawings. This is trends in atmospheric carbon dioxide. So I've just honed in on the last 1,200 years. Okay, CO2. On average, over the last 1,200 years or more, CO2 is 280 parts per million. Just goes along, 200, 200. This is the Industrial Revolution. And it goes up. The thing about climate change is I can't keep up with my figures. This figure only goes to 380 when I first got it. Current is 406. The figure's out of date. It's only a couple of years old. That's how fast things are changing. Here's trends in atmospheric temperature. There was actually a sort of a cool down over the last 2,000 years. Industrial revolution. Here's temperature today, 0.8 degrees C above pre-industrial revolution temperatures, and we're well on our way to 1. 2 has been determined to be catastrophic. We will pass that. Another example of a warming planet. So this is Arctic. That circle is just no data. And this is summer sea ice. Okay, minimum sea ice in 1979. About 8 million square kilometers. This is the extent minimum summer in 2009. 5 million. We lost half. That is, the sea ice is melting in ever more large areas, so the residual at the end of each summer, on average, is decreasing. So what? This doesn't affect sea level, because the ice is floating, just like an ice cube in your cocktail. When it melts, it doesn't change the water level in your drink. But notice the difference in reflectivity between the sea ice and the sea itself. The sea is much darker. So what happens is that incoming solar radiation that was reflected off of the sea ice is absorbed by the dark ocean waters. That water heats up. The adjacent coastline, the permafrost warms up. It generates methane gas. The warmer water accelerates. This is called a positive feedback loop, accelerating even more quickly the consequences of global warming. This is an interesting diagram that I picked up a picture that I got earlier last month. This is a NASA composite of historical greening of Canada. They just looked at the changes in land cover using sat images, and the green is more and more greening. That is a transfer from tundra, frozen, to a different landscape, different plant communities and so forth. As the climate warms, the plant communities are changing as well. And you can see up in the northern limit above the Arctic Circle, I mean, it's greening as a consequence of a warming world. And this will have dramatic impacts on coastal erosion as you move from permafrost to slushy sediment. If you've got archaeological sites that are sitting out there and land begins to heave and thaw and so forth, changing plant communities, the ecosystem interactions, food webs, all of this goes nuts. Another example, I saw this years ago, but maybe you've all seen these kinds of pictures. This is the Himalayan glacier in 1921. This is the exact same perspective in 2007. So that peak there is that peak there. You can see the ice was flowing. This is debris that was flowing right on down towards the ocean. Now it's all rock. The glaciers are receding in historical time. Now that water does go into the ocean. It contributes to sea level rise. melts on landlocked glaciers. That's water that once was in the ocean. It is thawing and returning to the ocean. This is triggering sea level rise in addition to the fact that as our world warms, the surface layer on the ocean warms and it expands. Thermal expansion. So over the last several hundred years, we've gotten sort of a thermal element, and now we're getting a true increase in volume caused by addition of water. This is the sea level curve. And if you're in this business, you will see these all over. This is one that was produced by the Southeast Florida Regional Climate Compact. In the purple is their range from 2011, and in the red, 2015. So what we have here is 2010 moving towards the future to the year 2110. And this is elevation in inches. I've got it here in meters. So when they first did this, they essentially said, all right, in 2011, sea level may reach about 1/2 meter to something under 2 meters. Now they've increased the upper limit because they're beginning to factor in all the meltwater. So those are these projections that people are creating in order to begin thinking about vulnerability and how do we plan. What elevations are we supposed to build our bridges at? What structures will be inundated over what time frame? And so on. Now for perspective, for the last 3,000 years, sea level was really stable. It was rising at less than 1 millimeter a year. And this is a time when all of our barrier islands stabilized, our wetlands stabilized and expanded, our estuaries filled in, a time when people were living along a stable coastline. Sea level was stable. And the coast was in equilibrium with that stability until recently. Today, sea level is rising at 3.4 millimeters a year, based on satellite altimetry data. Right? Almost 4 times faster, and you could predict that that'll cause some changes in the coastal zone. If we look at the range of over the next 100 years or so, it will rise at the low end at 5 millimeters or more than 20 millimeters a year. Why is this important? It's not only the magnitude here, over 2 meters, but the rate is important because the rate of change affects how the coastline responds, and especially living systems. For example, corals. They have to be in the photic zone. Mangroves, salt marsh, they have to be in the entire zone. If the rate of sea level rise occurs faster than they can keep pace, they go under. So we anticipate a collapse of a lot of the tropical coral communities and of wetlands, certainly at the higher rate, likely even at the lower rate. Reminded at this point that people usually, after the talk, come up to me and say, well, thank you, Dr. Doom, for that enlightening talk. But I tell you what, you got to start off with reality. This is real, it is happening now, and in our lifetime, we will be affected more than we know we are now. So here's an example of, and I was thinking about this, I'm a coastal geologist, but a large majority of the archaeological sites of indigenous are logically located along the coastline. You can move about easily, there's abundant food. This is a map of all 30 coastal states, and it shows whether the shoreline is severely eroding, moderately eroding, or relatively stable. And what you can see there is gray is sparse. This is a consequence, sure, of some urbanization, dredging, and harbor management, but in my opinion, the vast majority of this is a consequence of the sea level acceleration, which started 100 years ago. And this reflects changing equilibrium, a new dynamic equilibrium of erosion as sea level rises and begins to cut into stuff that before was above sea level. I think this is a graphic that really shows what Florida's facing. So this is DEP's critically eroding summary book or whatever. Length in miles of Florida's critically eroding beaches has increased almost 100%. So here they did 1989, they said there was 217.6 critically eroding miles of beach. Critically eroding means that the function of the beach is eminently threatened. The ecological function, the tourist function, the shore protection function, these are eminently threatened. Now look at 2015, 409 miles. Some of this is due to the management of inlets, but some of this is due to rising sea level. So we're seeing erosion. The second consequence, and you can think about this in terms of managing sites, one threat is erosion. The other is just flooding. So here is a king tide back a year ago or so. This is down South Florida where the elevations are low, and they'll point that out. But basically, you know, they didn't build these streets. Again, evidence of a warming world and rising sea level. So, Florida is especially vulnerable to sea level rise for three reasons. This is the first. Elevations in the coastal zone and southern peninsula are low and already subject to flooding during intense rainfall events, exceptional tides, and storm surge. Already, as we know. So on the left, you can see a topographic map of the peninsula, and everything in blue is less than like 5 meters, 15 feet above sea level. And I think it was mentioned earlier about South Florida, obviously has some serious reconciling. And then there's Miami Beach at a king tide, where they can't even, the roads are completely underwater. The second reason that Florida is especially vulnerable is its geology. The near-surface geology of coastal counties consists primarily of unconsolidated sand and porous limestone, through which water is easily transmitted. So we can't build levees, you know, and seawalls. The water goes under it. You know, it seeks its own level. So a lot of solutions that people are thinking about in New Orleans or New York now will not even work here. Miami Beach literally started to think about creating a concrete curtain that they were going to dig and inject over 100 feet below the surface. So that geological map, everything in yellow there is sand. The two pictures on the bottom is the Anastasia, which those of you from around here should be familiar with. I believe the fort is constructed from it. And on the right there is a Miami limestone, like Swiss cheese. So water just goes right through all of that. And therefore, we are even more vulnerable in states with a different geology. And lastly, of course, the Barrier Island system, upon which our tourism is based, is extremely susceptible to erosion and inundation with sea level rise. It's on the front line. And these will go underwater. So some examples of turning out just archaeology and so forth. This is how I did this for Kevin down in Sam's house, where the meeting was at Sam's house, so he helped me just put together a few of the sites that are in that area. Now this map, it's based on, it's a paper that I published, and I have the reference at the end. Basically based on geological history and a known relationship between CO2 and sea level, we project that for every 1 degree C rise in temperature, the oceans will rise 2.3 meters. Right? We're almost at 1 right now, 0.8, remember that. So in the system, inertia, in my opinion, is 2 more meters plus of rising sea level. So what these colors are, the darkest is a 1 degree, 2.3, and then as it lightens up to a 4 degree rise in sea level, which is entirely possible by the end of the century. What you see is all of the coastal archaeological sites, Windover, Turtle Mound, and so forth, are within the first meter, first degree. Some of them will go under by submergence if they're like Turtle Mound and Windover, because they're behind the barrier island and protected to some degree, so no attack by waves. But a lot of them, Air Force Base, Turtle Mound, these will be subjected to coastal erosion. Everything will ultimately go underwater. The next one, Cedar Key. Here we are at Cedar Key over here, right in the blue zone. And I picked this out from last year where a coastal erosion revealed an occupation site, and folks scrambled over there to try to catalog. And, but this is an example of a site being lost by erosion. And the 10,000 islands down at this location, everything's blue. That's just an artifact of the data. This is courtesy of Margot. We're down there with her. And these are the mounds and middens and so forth that, and this is LiDAR. When you look at that, it looks like, okay, I can get down there and do that. But then when you look at the photograph, like the lower right, it's not easy walking around in there. This is an example of an excavation in Vivacoring to try to get a handle just on the origin and evolution. I mean, from a geological perspective, where were these built? Over water? On land? Was it dry land? Was it wetland? We have no idea. And in this case, as you can see, they're fronted by wetlands. I can do this, I know I can. So, what happened to my, is it on there? Okay, can't do it. But right now, when sea level rises, those are not getting wave attack immediately because there's wetlands in front of them. As you can see here, they're sort of laid back. So the first thing that they're going to be threatened by is inundation. But eventually the waves are going to overtop and they will be threatened by erosion, as perhaps they have in the past, because you can see many of them have a straight seaward side and sort of tails coming off towards the mainland. And I think that's an erosional escarpment and so forth. It tells you that these are, the morphology and history is in part anthropogenic and in part geologic. So, what can we do? Current options. Do nothing. That's what we have done for the most part. Just do nothing. Just say it ain't happening. Say it ain't true. Protect and defend. Now this is, I did this for urban, but it's the same. You could be thinking about this for your sites, as I know you are. Protect and defend. In the case of, that is, hold the line. Do not let the ocean come in any further by beach nourishment, levees, berms, seawalls. You can accommodate. Now, this is Miami Beach. There's the old sidewalk. Here's the new one, 3 feet higher. They raised their roads. They raised their sidewalks. You have to go down steps to go into the front of the ground floor of stores now down there. But are there places where you could use accommodation? That is, elevate a site. Possible. Strategic withdrawal, managed retreat. I couldn't find an example of that. That's ultimately what we're going to have to do to preserve certainly structures. And again, something, I mean, I think all of these are options as you all move forward in planning for how to protect, preserve archaeological sites for future generations. Obviously, the first thing is to get in there and inventory, because it's a lot easier to do that above water than below, right? So, Dr. Doom concludes with this drawing, which I just picked out of EOS, just a couple. World energy-related carbon dioxide emissions forecast through 2040 will rise by 34%. Of course, this is India and China and so forth. This makes the less than 2-degree target to be reached by 2100, as agreed upon in the December Paris climate talks, ever more doubtful, right? So, in order to reach the 2-degree maximum, we already need to be making plans, and certainly by 2040, be reducing emissions, but we are not going to do that. So, in my opinion, we are headed for more than 4-degree rise in carbon dioxide, unless just a monumental change in how we manage our emissions as a global community. There's no evidence that that's going to occur. What you can do. First, keep informed of the science demonstrating climate change is real, happening now, and a consequence of humans. All right? Subscribe to websites like Climate Central, Daily Climate, 350, Skeptical Science. I have a Facebook page for the Space Coast Climate Change Initiative where I post relevant stuff every day. Just stay informed about this. And then talk about it. Talk about it as an informed person, a stakeholder. Get the conversation spreading. Don't be shy. I'm not. You know, you're all here, obviously, because you're not either. And when you talk about it, then that spreads. Be active. Attend meetings and events to show your support, number one, but also support of folks that are trying to develop adaptation and mitigation plans. Show your support. And lastly, vote. Vote your conscience. With that, I will conclude, and I appreciate your time.